All right, shader talk from, from our friends at DevSH.
All right, yeah. So I'm kind of sorry about taking up all the time. I'm Matt. I'm the CEO and CTO of the graphic programming. So we're a small computer graphics consultancy. So to quote Hitchcock, we should start with an earthquake, and the tension is to keep rising incessantly. So if you can raise your hand if you think this is CPU code, GPU code, or maybe both. Is it both? Well, the talk of the title of the talk gives it away. It's both. So hopefully everybody's awake by now. So hold on to your seats. So what we'll cover the state of HLSL for targeting SPIR-V, its compilers, the changes in DXC's functionality since our 2023 talk, what minimal changes DXC could make in the short term to best close the gaps between C++ and HLSL, how to keep the door open for another C++-like language that compiles to SPIR-V, so that's also an option, and how to create the C++ compatibility layer that allows you to execute snippets of HLSL on the host, and how to have binary compatibility between data structures. And the nitty-gritty details of including SPIR-V headers and boost libraries in HLSL, because shader compile times are just not long enough. And then there's a special bonus slide of look what you made me do, which is proof of concepts made with C11 templates, C++20 preprocessor, and inline SPIR-V. So I've got some completely impractical implementations of function calls and recursion. Then the gaps in SPIR-V and Vulkan specifications, which basically make certain things UB. Reese kind of touched upon it a little bit. And the discussion of the different tiers of function calls that I like to see in the future version of SPIR-V. So it's kind of like a please do this. And our compiler and like a standard template library that we packaged on Godbolt that you can kind of play with. So this is like a very big disclaimer. So this talk contains a lot of personal opinions about the state of projects from my own perspective. And I'm not involved in those projects as a maintainer, and I'm definitely not speaking on behalf of those people. So just getting that out the way. So 1 year has passed since our talk announcing our adoption of HLSL, and I can brief you about our experiences and results. There were going to be some risque memes here, but I decided that I do actually want to get invited to speak next year. I can confirm that DXC is basically truly the only production-ready compiler of C++-like dialect suitable for writing shaders of all pipeline stages, right? So what's the state? But the SPIR-V code gen in HLSL is a bit of a third wheel. And there seems to be a somewhat, at least to me, there seems to be a higher priority on pushing through new features like word graphs and shader model 6.8 in DXC. And there is that Clang HLSL effort, and it kind of seems to be at the same place where it was at the time of the announcement. I'm not dismissing the probable mountains of work that went into it so far, but from my point of view, when I want to kind of play with it, I still have an experimental compiler that I can't make a compute shader in, as DirectX IL, not as SPIR-V. But the upside is that Google has started working on the SPIR-V code gen for this new HLSL and mainstream Clang compiler. So at least we're now sure that SPIR-V targeting users of HLSL like us won't be left stranded indefinitely on DXC. And therefore the SPIR-V backend of that is no longer what I called a yet to be assigned to do in 2023. And obviously kudos to Google for keeping up with the HLSL to SPIR-V effort, despite the Stadia shutdown. Now SYCL presents a very nice CUDA-like C++ language with Clang LLVM. It compiles it and SPIR-V for Vulkan, and there's like a Vulkan environment, like runtime that can run your SYCL. But this is similar to the OpenCL and Vulkan approach, which was just talked about. You can't use that for graphics or ray tracing pipelines. It makes about as much sense as attempting to use CUDA. Like, it's not possible. So obviously, GLSL is currently the standard for expressing new SPIR-V functionality, and it's still getting work done. But don't hold on to don't hold your breath, waiting for some new language syntax or something like that. It's still going to remain what is essentially C without pointers and references. But despite all this, well, HLSL 2021 is actually production ready. So the key is kind of managing your expectations and take into account that it's a fork of Clang 3.7, and that code base is like 8 years old, and it's a production compiler, so it's getting maintained, and it's nice that it doesn't get broken. The maintainers are very helpful, and the community, because of all of the whole effort is kind of on GitHub, it can provide you with workarounds, right? So if you want to do 64-bit image atomics, and ask about that, somebody's going to come up with a way to do it. And Microsoft does actually spend its own time and its own engineers' time on the SPIR-V code gen. And they have pretty nice inline SPIR-V that you should definitely learn about and use. There are certain very important language proposals that actually do get implemented in DXC instead of waiting for Clang. So there are two which are very, very important, which is the new inline SPIR-V and the buffer device address. And in my opinion, there is no alternative that's closer to C++ that's actually tested, right? There are some things like, Circle and so on, but, if you want to see something that actually gets used by a lot of people and, is open source and maintained, this is your only option, right? And most of the things you don't like, you can actually work your way around, and I'm going to show you some of those things. And the big Achilles heel is that anything else really gets blocked by proposal 6. And now, what are proposals? So per the 2022 announcement, the evolution of HLSL as a language is open to the public. So there's a separate repository, basically, for HLSL proposals. And right now, there are like 13 proposals which are actually written up and under consultation. Under consideration. And there's 56 issues open, which are just like random ideas that are not fully kind of spec'd out and formalized yet. So I'm only going to discuss 3 of the proposals. So this is the only one that's not under active development. So that's usually why a feature can't be done. So when DXC was created, they basically took Clang 3.7 and removed a bunch of stuff, right? And there is a notion, so there's no notion of a reference or a pointer in a particular address space. And there's a very weird calling convention, which I'm going to expand on. Just because there's no references in the language, it doesn't mean that the compiler actually isn't like kind of creating them under the hood. So you can actually see types with the ampersand in template errors when you try and kind of do something that's not syntactically valid. And HLSL has non-static member functions and operators, but you still can't stick a const at the end of the definition. And at the time of the HLSL 2021 announcement, the DXC supported a lot more operators than it does currently. Like, for example, conversion operators or like increment or something like that. But the thing is, like, those actually rely on you having a notion of a reference, so they have to disable them. Also, don't tell anyone that I told you that declotype exists in DXC. I'm kind of scared that they're going to take it away from me. So a lot of people think about out and in-out being references in shading languages. So what do you think the value of T is after that finishes execution? Anyone think it's 1? Anyone thinks it's 2?
One of them.
Actually, one of them, yeah. Exactly. It's either 1 or 2. Actually, HLSL and GLSL, they behave differently. Like, they actually have the same calling convention it's called return by value, so value return. And they actually written up what it is in the LLVM project. And by accident, the GLSL happens to produce the expected result, but don't trust in that, because in GLSL slang, right? They actually get you get temporary copies, and then they get copied back out at the calling side. So if you change the order of A and B assignment inside of that function, you're not going to change the value, right? Because it's basically copying out A first and B first, like or the other way around. But it only depends on the declaration order in your signature, not on actually what the function does inside. Whereas DarkX shader compiler has this thing where it's basically treating every single in-out as or an out as a restrict reference. So, and this is kind of the funny thing, because it's SPIR-V doesn't really care about this. Like, if you wanted to have, let's say, aliased references, you could do it in just plain old SPIR-V. And it gets worse, actually. So because it's a value return convention, you can actually pass a in-out of a different type. So you can pass a variable of a different type than the in-out declaration. And as long as it can be explicitly, like implicitly converted, it will. So you'll end up going like, oh, you know, like a float gets casted to an int on the way in, and then there's some stuff going on, and then it gets converted on the way out. And you also have this little gem, which is there's a very big performance difference between making that little array a global, which kind of comes from the outside, or passing it around. So if the compiler can't figure out which elements you're tapping, it might just copy the whole array in and then copy the whole array out. So this is why we kind of use this accessor pattern, which is just like a big lambda, which can access globals. So I guess you kind of starting to see why we need references. There is a kind of stop-back crutch solution in DXC where you can, when you're writing SPIR-V intrinsic, there's a special attribute that you can put on a particular on a particular variable, but it only works for the intrinsic. You can actually pass it around. So if you then wrap that intrinsic into another function, then you lose that that ability. If DXC actually implemented value return properly the way that the GLSL does. So it's kind of a bug, but it works. So for now, in-out is a reference, but there is a pull request where they want to fix that and have that compiler behave in a spec-conformant way. And in that case, you get a temporary, and then that breaks how in-out works currently. So, yeah. So proposal 10 is buffer device address. So the current state of row buffer load and row buffer store is they used to disallow non-plain old data types, and then that silent, and then somebody then enabled that to happen on structs. This silently produced bugs where you needed to like load members one by one, and now it just plain old fails code gen if you try to use it on a struct. And there are a few other issues, which is that an upload gets issued instead of an access chain when you, for example, load a struct and then a member, at least back when it used to work for like a little while. And then that would not be compatible with atomics because you don't have an access chain. You're kind of trying to shove a temporary variable that you loaded a member into while you're calling an atomic function. So yeah. Now, the problem gets compounded by the fact that the inline SPIR-V that it's currently in DXC does not allow you to kind of just work your way around that by just writing your own SPIR-V intrinsics. I did attempt this. You can kind of have a look, and it's the inline SPIR-V is not complete enough for me to be able to declare a pointer type in SPIR-V. There is proposal 10, which is actually by Greg. And Greg, I just learned, is retired, actually, so he's formally Lunargy. So it fixes that whole buffer device address mess, and it introduces a VK buffer pointer. And it's almost perfect. We will probably wrap around that because after consultation, they made it restrict by default, which in my opinion, it basically brings you back to this little, it brings you back to this little gem. So I'd rather not have them restrict by default. And then it doesn't provide the Boolean comparison, etc. operators for the pointer, and also you can't really take an address to a member, so you kind of need extra glue to make that work. And that brings us on to the HLSL inline SPIR-V proposal, which is proposal 11. So basically, the current inline SPIR-V sucks. So the most basic usage of inline SPIR-V is to be able to generate the SPIR-V you want verbatim. For example, this is an atomic add instruction, and you can see that from the SPIR-V kind of headers enum, you can kind of see which instruction exactly it is. But you might also want to expose things which are other than just SPIR-V functions. Like you might want to declare an extension or capability that's used, execution mode. You want to declare new SPIR-V types. So this is like the current existing syntax for doing this. Now, the problem is that you need to give this type integer ID, which is unique, and you need to keep track of it. So you can't really template that. You can't really automate it anyway. And for a given type, there's not a single ID that you can give it. So for example, there is an op type instruction to make a physical pointer, like buffer device address, to a particular struct. And then what you do is you combine the struct definition with the pointer type declaration. So for every single kind of different struct that you use, you need to construct a new SPIR-V type. So, and then for that, you would need a new integer value. And obviously, DXC has no clue about the storage class, which is allowed on this new type. So you can't really do anything, like you can't store it, it's opaque. And there's a bigger problem, which is that the last two, the last two, so the execution modes and the SPIR-V types, they aren't really attributes that you stick on things, they're function calls, and they need to be statically reachable from your entry point, which just opens up a whole can of worms. And you get proposal 11, which is better inline SPIR-V. This fixes everything on the previous slide. Everything is like basically type defs. You can template it really nicely. You can actually declare the size of a type and the alignment. And the storage class is an attribute. Sorry, storage class. I think I've got a typo there. It's storage space. It's called the storage class. And execution modes are now attributes that you put on functions instead of having to kind of call this special intrinsic that doesn't do anything, but it still needs to be reachable. And then it also fills in other gaps, which is you can declare SPIR-V built-ins. So for example, the GL num work groups, the equivalent of that, and also stage inputs and outputs. So when you have a shader stage, you've got those in-out variables. You can also declare those as statics. And I don't know if you noticed, but in all of this, I'm using the actual SPIR-V enums, like from the headers. So we actually do include SPIR-V headers into HLSL to actually have this, because they're constant, and you can actually put them in attributes, and it works. And the only thing you need to do is just you need to disable the global operator overloads, because that's something HLSL does not really support. And we also want to auto-generate all of those intrinsics in the future. So how to make your HLSL compile as host C++? It's kind of easy. You can just make a compatibility headers, use a little bit, like a tiny sprinkling of macros. The hardest part is actually getting your access to HLSL types and intrinsics in C++. I've been looking for this for many years, and this was always complicated by the fact that a structure has a different alignment in let's say, GLSL, STD 140 or STD 430. than it would have in C++. So you get weird things like a vec3 has a size of 12, but an alignment of 16. So if you just use scalar layout from Vulkan, which is pretty much ubiquitous, that just makes it pack normally like it does in C for uniform buffers and for SSBOs. And then, yeah, just a word of advice, probably stick to row major matrices and just kind of wrap the GLM type so that you don't notice the fact that you're working on a constantly transposed matrix. And the rest of it is just type defs and aliases. GLM is really good for this. And use size types while you're at it, like float 32, float 16, float 64, and so on. And the HLSL is actually really nice because now all of the vector types and the matrix types are actually templates, which makes interacting with your C++ code a lot easier. And if you need float 16 on the CPU, there's a library called IMAF from OpenEXR. And the float 16 implementation is pretty solid. And you can actually use it in place of an actual scalar in the GLM types. So how close can you get to host code with SPIR-V? So the year is 2024, and every desktop GPU is getting a driver updates. That's getting driver updates from their IHV. They support SPIR-V 1.3 and 1.6 and Vulkan 1.3. So we did make a profile. Christoph. And basically, here's all the stuff that you can do. So 8 16-bit storage you can do. A buffer device address, also ubiquitous. I'm talking, of course, about desktop, not mobile. And scalar layout, again, as I said. And the nice thing about DXC is actually it always has capability stripping pass during its SPIR-V legalization. So just because you declare a float 64 doesn't mean that the shader will actually require that capability, because it will get stripped if you're not statically using it. There's just a word of wording that there is like an allow list in there. So what it strips has to be like explicitly greenlit for stripping. And so you might sometimes have to open a PR or something that says, well, this is actually okay to strip. And the problem with HLSL for now is that there's no int8 type. So this is actually what this really small header of compatibility looks like. It's not a lot. So we made a template library in Nabla, and we basically include the Boost preprocessor library in there. So it's like a macro library where you can do like repeat stuff and so on. I also wanted to include Boost metaprogramming library, but the problem is that HLSL has no const or const eval. So we have to make our own with integral constant. And the SPIR-V headers are basically also as an include. And work in progress is getting like a GLSL compatibility header as well, where you basically have functions that have the same names and syntax as GLSL that kind of either map to SPIR-V intrinsics or to HLSL stuff. And also exposing most of the SPIR-V GL450 STD, which is stuff like square root and length that also work in doubles, because HLSL doesn't have that either. And the full cherry on top is the parts of C++ STL. It's obviously quite big. So for example, we've got type traits with templates, numerical limits, algorithm, like upper and lower bound. I'm working currently on functional, type generic math, and complex, with some adjustments to kind of account for how HLSL differs. So we actually needed to make like a compiler executable for this, because now that we kind of have all this code, when we work with RenderDoc, it's kind of difficult to rebuild that. So what we did is we wrapped up DXC, the actual compiler, with all of the headers that are built in, and now there's basically an executable which you can kind of use as a shader compiler, which forces all. First of all, it forces all of these flags, and then it also has the standard template library. All of the headers that we have built into the engine also allows you to use them. And we have like a special pragma which lets us kind of back up the flags that we used to compile with, so you don't have to kind of mess around and run the doc to replicate this. I do have a demo that works, but just because of the way that we're recording this, I can go back to this and click on it at the end. We have our self-hosted Godbolt instance where we've hooked up this executable so you can play with it yourself. So yeah, C++11 templates and the preprocessor are actually quite powerful. You can actually preprocess your shaders independently of your shader compiler, be it DXC, Clang, or HLSL. We can tell you to just use BoostWave as your preprocessor because we've tried others, and ShaderC and GLSlang, they have no variadic macros and some bugs. DXC has no way to hook up a virtual file system to resolve includes. And we tried some header-only preprocessors, and they just basically have issues with basic preprocessor logic. So why I'm talking about preprocessor when I seem to be hailing templates as the final replacement? So this is why I include Boost preprocessor library in the HLSL. So since C++ reflection and commercial nuclear fusion are eternally just around the corner, the Boost preprocessor macros are currently the best way to kind of generate this kind of special tagged reflection. And so due to having a virtual file system, we require that any runtime compilation has to be like a Unity build. So all of the includes need to be resolved. And that interacts with the preprocessing logic, because whether you include something or not depends on the preprocessor. So initially what we used to do until 6 months ago is we used to turn off all of the preprocessing and just let the includes go. So it means that we even disabled the preprocessor guards. So we had actually like a counter of how many times a given include included itself. And this didn't scale well, and it basically led to reproduction cases that had like 250,000 lines of GLSL code. And the problem is that the Boost preprocessor library, it actually relies on the preprocessor and includes and conditional includes and so on to do all of the work. So we knew that for the next compiler we'll target will be based on a recent version of Clang. So we should expect regular precompiled headers of C++20 modules, and all of them work on abstract syntax tree serialization, which means that all of your preprocessing flags, they need to remain constant. Because if they don't, then your serialization is no longer valid. So how do we specialize the shaders now? So we made the device capability traits. And what this does is, if you define a struct which has these members, we can check that the struct has these members, and you can pass this as a template parameter to a function. So for example, here, if you want to do an inclusive scan on a subgroup, whether you can do it in an accelerated way with the subgroup arithmetic, or whether you need to use a shuffle and a strong co-gather, depends on the capability of your hardware. And we take the capability of hardware as a template parameter. So apparently you can't have recursion in HLSL. Seems not. Please don't do this at home. This is awful. I thought about if I could, not if I should. This compiles only with 0 optimization level. If you go optimization level 1, your SPIR-V optimization will just time out. Like the compiler is going to die. And it generates a lot of SPIR-V, and if you actually lower the number of times it's allowed to recurse, then it will just generate a humongous amount of SPIR-V. So this is obviously a massive cry for help. So how about we just have function pointers in SPIR-V? It's not like GPUs can't do function calls, or at least subgroup uniform jumps to arbitrary addresses. I mean, if the GPU already can implement rate pacing pipeline, it can jump to a function, right? In an SBT. NVIDIA could do it. AMD could do it. Tomasz Stachowiak showed this with GL get program binary like 10 years ago on AMD. You can, of course, do all sorts of compiler magic and kind of emulate function calls, but it really shouldn't be needed. So I made a little suggestion. You can probably upvote it. And there's different tiers of function calling capability that I kind of suggest that we could maybe start with the top one and kind of work our way down. And obviously, the next speaker after me has written really good blog post about this. So Reese has talked about the parallel prefix sum, and I'm running out of time, so I can't really go into it. I'll leave the slides. But basically, there's some issues with forward progress, and you can reduce the amount of workload that you can do, but you can't have work groups wait on other work groups. Like the algorithm needs to be lockless, or it's UB due to lack of forward progress guarantees. So yeah, I mean, this is like my wish list of what I want DXC to do in the very near term, and what it could really do in the very near term. I would like to have context function references, because then you can kind of specialize in the way that you do with struct functors, because all of the functions are static. Unless you export them, you can know their address at compile time and take context references to functions. And variadic templates are something that is really, really missing. And const-eval and context, because that's why we kind of need to do all of this dancing around and use std integral constants to kind of implement everything instead of just doing it the normal way. So yeah, this another kind of thing which you can look on your own time, which is me trying to emulate BDA in DirectX